大家好，我叫崔云社。这视频将和我的物理课有关。我的物理老师叫姚老师。上课的时候，姚老师常常把我们叫新概念。我们的作业是课文里的问题。这是我的物理课文。现在我们正在学电压和阴电律。这两项是通过法拉第定律和冷子定律来讲解的。在这视频中，我将简单的分析和解释这两定律。当磁场超过电流的部分，这将感应电流流动。这节非常简单。希望你能享受和欣赏这视频。
Okay. Now I want to introduce myself in Chinese. 你们好，我叫姚飞，我是这个 AP Physics 的teacher， 我现在的老师，我在这里教了25年了。我从中国来，我从北京来。Okay. Thank you for listening. Suppose let's sing this one. Okay, I am using this one as my way to figure out what will be the direction of the induced EMF. Okay, let's look at this one. I have a long straight wire, this one carrying a current I. Everybody is okay with me right now? Okay, I have one circuit loop, is a rectangular circuit loop with resistance R connected in the circuit. If this is the case here, do you see that in this area, I should have the magnetic field? True? The field is created by this one here. What is the direction of the field? Everybody see the field goes in? Yes? Okay. So my field goes in. That's the field created by this current, right? That's my field. Now, what I want to say is this one here. Suppose my current here is decreasing. If my current is decreasing here, what do you feel? My dV dt. My flux, is my flux increasing or decreasing? It must be decreasing. Okay, so this one here basically will be less than 0.
Why is it decreasing?
Okay, because this current here is decreasing. This current is decreasing will cause a magnetic field decreasing.
Okay.
My area doesn't change, so my flux is decreasing. Agree? If that's the case here, I want to say that my induced EMF equals negative dV dt. What does that mean? Will be my induced EMF should be positive. Agree? Yes or no? Do you agree with me? If you agree with me here, now this positive EMF means what? Means that my induced EMF is in the positive direction of my circuit. But what is my positive direction? What I say here is, once again, this is my magnetic field here. If I choose the same direction as my normal here, then I will say that I will be able to have my flux is positive and the radius of the beam will cause the radius of flux, right? So in this case here, my normal is also choosing in that direction here. So do you see that clockwise here as my positive? Yes? When I have this one is positive here, basically what I realized that, okay, I will be able to get my induced current in this way here. Usually they will ask you, on the resistor, what is the direction of the current? You can say that. In the resistor, the current will go from right to left. Correct? In the resistor, the current will go from right to left. see. In this case here, okay, all the part actually is the whole thing. Yeah. So the current will go to the direction here. In that case here, the current will go in the same direction as the input.
So like the delta between any point is zero?
I see. Is the delta V between any point is zero? Actually, this is a different case here. The delta V is not going to be zero. The delta V is going to be the whole integration of this one here. The electric field times this one here will equals your induced EMF. I think I may need to come to this one here, introduce this one in a little bit, because that one here will change our way of thinking about electric field. Because previously, I believe we talked about electric field is a conservative field, so that was zero, right? And now we're talking about this one here. So this jumping here actually is a little bit. I think I need to save some time to talk about that jumping. Okay. Keep in mind that there is some real. Okay, this one here actually will, when next chapter here we're talking about Maxwell's equation. We'll talk about that. Questions? Yes? No?
I'll be solving a problem that uses the concept that you saw in the video earlier, which is Lenz's law. And Lenz's law states that the induced current is always such as to oppose the change of flux that generated it. So basically what Lenz's law is, it tries to keep the coil in its original state, so it opposes any change in flux. So the problem that I'm solving is, let me read it really quick. The bar magnet shown is thrust through the coil at constant speed. Consider the following stages: A, when the North Pole approaches the coil, and B, when the magnet is centered in the coil. What is the direction of the current in the resistor at each of these stages? So right here is the magnet, South and North Pole. So for A, when the North Pole approaches, so this whole magnet is moving that way, right? And since it's the North Pole, it moves the magnetic field, goes outwards, and since it's going closer and closer to the coil, that means the coil would want to oppose the change, so it would try to create an EMF or a voltage that would oppose the change of the magnetic field that is created by the magnet. So in order to oppose the change, using right hand rule, the magnetic field would need to go that way, which is my thumb. And then since the current wraps around like this, the current would need to go this way. So it would travel from left to right to across the resistor. So this is left to right. And for B, when the magnet is centered at the coil, so this case the magnet would be inside here. This is the magnet inside, and it's not moving. And the answer to this question is there is no current across the resistor, because since it isn't moving closer or farther away from the coil, and it's constant and it's just staying there, Lenz's law doesn't apply because there is no movement or there is no change in flux. 谢谢你们听我的演讲。